Okay. So just a reminder, your homework is still due, nothing has changed. But we have more things that are needed from you. So if you remember, we had talked about at the beginning of the class, the class project. Here are the deliverables that are going to be due along the way. So this is the end of roughly at the end of a month into the class. That's Feb 24. You have a proposal. It's a 2-page project proposal describing what you're going to be working on. It's a few weeks out from now. I recommend making use of the office hours and talking to us if you need ideas. Eventually, we're going to have at some point midway presentations and at some point the final. It would be nice if you do it in groups of 2. Anywhere one can be spawned by us. Anything larger than that, it just becomes an unruly mess. So 2 would be ideal. So here's what we're expecting in this proposal. So put it in NIPS format. That's a conference, Neural Information Processing System. That's the machine learning standard conference format. We want you to think of, it's just a 2-page document, it's a light document, which we want you to address these things. Tell us what you're working on. Your project idea should be roughly like 2 paragraphs. Tell us, I'm taking this data set, I'm applying it on this problem, here's what I'm working on. There's an actual section, your data set details. So I'd like you to exactly specify what data you're going to be working on. If it's a standard data set that's available online, list it out, cite it. If it's something that you're collecting in your lab, just briefly describe it. It would be nice, and I want to emphasize that it would be nice if you already have the data to start off with. You don't want to spend an entire semester collecting data and then at the end of the semester not have anything running. So you have to specify what data you already have that you collected. Software. So you have to tell us which libraries you'll use, what piece of software you'll write. It is okay to use external code. It is okay to use external software and libraries, something else that in your lab has written or something that's publicly available. That's fine. You have to explicitly list it out. Here's what I'm using from someone else. Here's what I'm planning to write. If you're planning to implement some papers, tell us what papers you're planning to read and write. We expect you to have read these by the time you submit the proposal. Don't tell us some papers that you haven't read and then you'll be surprised about it. If you have 2 or 3 people in your team, tell us what the breakdown of labor is going to be. And this is really important. You have to tell us what are we holding you accountable to. There is some mid-semester milestone that you have to reach. So break down your task into 2 or 3 or 4 steps and tell us where you will be at the mid-semester milestone. Okay. So let me just say there's, usually, I've said this before, but there's 3 broad categories of projects that we end up seeing. There's a survey kind of things where you're interested in some domain and you'll apply a bunch of methods to a particular problem. You'll see which one works better. There's the formulation or development thing where you're interested in a particular problem. You have some data and you'd like to formulate it as a clustering problem, as a classification problem, as a regression problem. You think decision trees are really great for that. Good. That's a perfectly fine project. Describe it out, flesh it out, tell us exactly what you plan to do. And then there's of course the more theoretical projects where if you're really interested in machine learning, you're trying to analyze some algorithm, you think that you can make improvements, you can create new algorithms, great, that's also well. There's a web page up here that has some ideas for some bias sampling of ideas from things that I'm kind of vaguely interested in, and some ideas for data sets. If you're running short of ideas, feel free to get that. The rules, just to recap. I have to say this, I feel like I have to say this. Your project has to be about machine learning. It cannot be about anything else. It has to involve real data. I run into this because every so often I have a few communications people in my class and they insist on running simulations, and that's all kosher in that domain. It would be nice if, it'd be really nice if you have real data. If you cannot have real data, if you think you need to have simulations, come talk to us. Come talk and we'll figure out why you really need that. It's okay to apply, it's okay to combine this with other class projects. If you're taking some other classes, you need explicit permission from both. And you need to list out in your proposal what you're doing for the other class and what you're doing for this class. Okay? And as I said, it's okay to use existing libraries. The key thing being, more thought and effort implies more credit. If you end up, I downloaded this library, it was already set up to run it on this piece of software, and that's my project. Well, I'm going to run shortcuts on grading as well. So that's going to be the effort I put on. Okay. I thought I'd show you one from a couple of years ago. Here's roughly the kind of thing that we're expecting. Tell us, broad outline of your ideas. Give us some details, what methods you're applying. I'll use this data set. It would be nice if you cite it. I'll use a combination of MATLAB, C++, Python. I have existing code. I'll use OpenCV and Piano libraries. And here are the papers that I'm reading. Okay. And for the mid-semester milestone, I'll have this implemented. Then I should have started this. That's kind of what we're expecting out of your. Any questions?
So, yeah, I have a question.
Yes.
So, do we choose one idea from a pool of ideas, or we come up with our own idea?
Either one's fine. You can come up with your own. There are some suggestions on the website. You want to pick one.
Can my project be an application to improve a computer vision project?
That's good. Improving a project that you've done before, but with something that you're doing this semester, okay. And it has some machine learning involved. Okay. Yes. Okay.
So since the proposal is due probably in 3 weeks, then the project should use something that we will have seen by then.
I mean, so there will be a little bit of self-study involved here, right? It's okay to say, I don't know everything, but I'll read up on this. Okay. That's why you're listing out, here are the papers that I've just gone over. I understand this is applying it to this idea. I'm going to read this more in detail. I'll know more when we cover related concepts in class, and I'll implement this, and this. Okay. Don't wait for that topic to be covered in class before you can pick up a project. Yes, is there another question? Okay, and come talk to us if you're unsure about what you're working on, and if you need ideas, come to the office actually. All right, so that's due in a few weeks. Okay, so last time we had finished nearest neighbor, and we stuck pretty heavily to something that we were calling this procedural view of machine learning. That there's a training stage and a testing stage. In the training stage, you sort of learn a mapping from X, Y, you learn what that F is, and then testing stage you apply. And in nearest neighbor, we kind of cheated, we didn't even learn that, right? And this time, what we like to switch to, we want to go towards classifiers that derive a little more theory with probabilistic reasoning. So we're going to go towards naive Bayes and logistic regression classifiers, and we'll also look at probabilistic models for regression. Those are both naive Bayes and logistic regression. Confusingly, despite having regression in its name, logistic regression is a classification algorithm, but we will also look at some probabilistic regression. So what we'll need to do there is we'll need to think about a joint distribution P of X, Y, and we'll need to think about the data that we have in front of us as samples from this distribution, and we'll need to infer something about that distribution. We'll need to assume what kind of a distribution is this. That distribution maybe has some parameters. Maybe you need to learn some parameters in that distribution. Right? So that's going to be the view that we're taking, and that's why the hope will be once you have learned some parameters of this distribution, you have some hope of generalizing to a new data set which is also sampled from the same distribution. So there's always going to be this assumption that the data that I'm seeing in future is coming from the same distribution that generated the data at the training time. There are often, this is especially true in online applications or things where data comes streaming in, that what happens is that the later data samples are actually coming from a different distribution. The thing that you're trying to learn has changed. but we won't get to that yet. Okay? Right now the assumption is that the test set is sampled IID from the same distribution. Okay, so in order to get there, we need to start simple. So the plan for today is let's have a brief review of things that you should already know, which is probability distributions, mass functions, densities, joints, conditionals, marginals, Bayesian priors. Okay, these are things that you should already know, but let's look at them so that we can sort of have our notation down, so that we can make sure that everybody's on the same page. And this class and this lecture and next lecture, it will feel extremely silly that I'm trying to say we will solve span classification or image recognition, or I will derive motivation from AI and then we'll try to fit like a coin toss model, right? It feels like there's a large disconnect between the goals that we claim to solve and the sort of models that we'll end up starting with. But the thing to keep in mind is that that same theory that we develop for a simple coin toss will apply to all sorts of sophisticated models that you will see on in the future. So it's extremely important to get that. It's important to eat your vegetables. It's important to get that down, and then we will do the cool stuff after that. Okay, so just a historical note. It's actually in retrospect today, probability feels like an extremely natural concept for us. And in machine learning, you cannot pick up a paper today without some reference of some probabilistic model or some reference to probability or statistics. But it wasn't always this way. If you go back to some of the earlier works in AI, especially, the probability was largely absent. In fact, there was a huge split in the communities of AI and statistical learning, where the argument was that brains do symbolic manipulation, not integration or daily probability. The idea was, if we have to reason about intelligence, we have to do sort of symbolic manipulation and logic, and not worry about probabilities and variance. The world has come around. This is machine learning today, and is making, especially in probabilistic learning and statistical learning, as sort of those are some of the most robust systems that we have today. Okay, so let's start extremely simple. Probability. Everything starts with an event, something that you're interested in. A is an event. Let's say that event being that your next patient has cancer, or Rafael Nadal wins French Open 2015, which I'm interested in seeing, but let's see. His performance has been extremely weak. Okay, so everybody has met probabilities before. Let me ask a question. What does probability of A mean? Yes?
It's a proportion.
It's a proportion. Proportion of what?
Of the times A happens compared to the total possibilities.
Very nice. Okay, so what we have here is a frequentist in the crowd. This is the frequentist view of probability. It's the fact that probabilities are limiting ratios. So the proportion that there is a repeating non-deterministic event, and the number of times that event is true or happens divided by the total number of times you repeated this experiment, and that limiting ratio. That's an extremely frequentist view of probability. Not extreme, that is the frequentist view of probability. It says that you have to have something that can repeat. Under this view, what is the probability that Rafael Nadal wins French Open 2015?
It's like how many times he won with the last, how many, like he played like 10 times. But
that's not the event I'm interested in. The event I'm interested in is French Open 2015.
We cannot win French Open a lot of times.
You cannot repeat the French Open, you cannot win the French Open too many times because you cannot run French Open 2015 many times.
Yeah, at the same time, you have to introduce a condition. You didn't use during open, so
but so far, no, running to conditional probabilities. No, come on. We're just trying to understand.
Check history, maybe.
Check history.
How many times you could run before?
But how does that fit into this definition? Right? The definition says I have an event. I should be able to run it infinite times, and look at the ratio, the limit of that ratio. So this definition fails to work when you have events that are non-repeatable. You cannot talk about the limiting ratio of events that you cannot have. You know, the probability that the weather tomorrow will be sunny, where tomorrow is the particular date, not just any tomorrow, which it could be. Right? You cannot reason about that. So there, the other view comes into mind, which is the Bayesian perspective on probability, that the probability of A is just your belief about the event A. Okay? Interestingly, the definition says nothing about whether or not that has anything to do with the real world. In fact, you know, oftentimes you will meet people whose beliefs are extremely, you know, separate from the real world. They have nothing to do with what may or may not happen. So it's just, you know, it's a system of algebra that lets you reason about your beliefs in some consistent way. Right? You can say that, you know, the probability that Rafael Nadal is going to win French Open is 0.9, and you're crazy. That's not going to happen. But you know, that's a perfectly valid view of probability. There's actually a third interesting view of probability, which is the market design view. If there was a market where you could purchase a share which would pay out, let's say, $1 or $10, what money should you pay? How much should you buy that for? This actually, you know, there were markets that, you know, ultimately got shut down. So this is the latest picture I could find, because this was from the 2012 election. But you can, the event is 2012 elections, is Barack Obama going to win or Mitt Romney, right? And the market price for the, you know, if you pick the winner, at some point the event will come true. If you're held with that share, the market pays you a payout of $10, and here's the current price that the market puts at that share. Right? You can buy shares at 620, which means that the current probability that of the market is that they believe that Barack Obama will win is 62%. So this view helps you incorporate wisdom of the crowds, if you will. If there's one person who has side information that others don't have, if you know tomorrow that this event is going to happen, today you will continue to buy these shares as the prices rise because you're buying. Right? Even if you buy them at $6, tomorrow you will still make 4. Even if the price rises to 7, tomorrow you will still win 3. And you continue to buy till you drive up the probability to where you believe it should be. Right? So that's the market view of probability. So those are 3 different views of what the probability of an event could mean. For the purposes of this class, we won't care what you believe or what they mean. It just won't matter largely. The reason why it won't matter is as long as you work with the axioms of probability, it doesn't matter how you view what the numbers come out with. Right? So as long as you follow the axioms of probability, it will be fine. What are the axioms of probability?
They add up to 1.
Should be less than 1.
Okay, probability of something should be less than 1. You got 1 down. It means 0, 1. Okay, that's much better. That would be nice. Otherwise, the probability is negative. Okay.
Probability of an event and its complementarity, so one minus the other.
Is that really an axiom, or can you derive that? Oh, yeah, that thing, that class we took. Something.
Sample space should add up to 1.
Sample space should add up to 1. Yes. Okay. So you got one more axiom now. The probability of it's a function that assigns a value to any event. The value always lies between 0 and 1. The probability of the empty set is 0. Probability of everything is 1. And crucially, you can do some algebra on it. And that's it. Those 4, if those are valid, it doesn't really matter what those, as long as you come up with a function that takes a set, gives it a number, satisfies those 4, I don't care how you came up with it. Whether you fit it with data, whether you ran an experiment infinite times, whether that's just a number that you came out of your hat and you say, I really believe this is it. Or whether you ran a market and people bought shares, doesn't really matter. As long as those 4 hold, it's a consistent system of algebra. Of course, this, like any garbage in, garbage out system, if you input beliefs that are completely uncalibrated with reality, what will be output is true under your system of axioms, but also inconsistent with reality. And this is going to be important because we are going to be building quote-unquote Bayesian classifiers, where you will have to write priors or beliefs about what you think is true about some categories. So, for example, if you're trying to do cancer classification versus not, you will put in a prior probability of how often do you believe people have cancer, just without seeing any symptoms or anything. Right? And if those beliefs are uncalibrated with reality, the output that you get from a classifier will also be uncalibrated. And that's why it's often going to be important that just because you see a paper has a lot of fancy math, does a lot of derivation, and outputs a probability, here I have a number and it's a probability, therefore it has to be correct. Yes, it's correct, but it could be uncalibrated, right? Because the input assumptions that were made were incorrect. Right? Okay. All right, so what do the axioms mean? Roughly, let's keep this in mind. Let's go over this quicker because we know this. The way to think of this is, the set view is extremely nice to think of this. But there's a space, there's a world, and we're looking at the fraction of the worlds in which some event is true, and that's why the fractions can only be between 0 and 1. If that thing never happens, then the probability of the empty set is 0. That's why the sort of area of that event is 0. If it's everything, then the area can't get bigger than 1. And there's some system of algebra, right? I can, in the set view of things, it's extremely intuitive. If you want the probability of A or B, which is the union, so if you want to calculate the area of this whole thing, you can calculate the area of this, and now you're overcounting this, and so you subtract that out, and that happens to be the probability of the intersection. Okay. It's extremely simple algebra of these things. Okay. So now that we've gotten that, it's often going to be much easier to work with random variables. So you'll define some sample space and you'll work with some random variables. So let's get some of that notation down. We broad classes of random variables, discrete and continuous. Let's say you're solving a classification problem, that y is going to be discrete. In this case, I've written x. We will use this notation. So capital X will be the name of that random variable, right? That's the class, does this patient have cancer? Or it's the feature, is this house near a hospital or something like that, right? And we'll use this notation, cal X, obviously not on the board, use value of X, which is the sample space, or the set of possible outcomes. And I'll use the little x to mean the actual outcome that we are talking about in an experiment. So this is standard probabilistic notation. And we'll talk about, for discrete variables, mass functions, probability mass functions. So this is going to be the full notation. This variable, which means, is this email spam or not? Is its state set to 0 or 1, where little x is 0 or 1, right? And tell me a number corresponding to this assignment. And often, to save space, we will just use a short form. So we'll use this p of x, where it's clear which variable we're talking about. It feels like this is extremely pedantic, but this is going to be useful when we start doing derivations. We lose track of which variable we were working with. So when it's clear which variable we were working with, when it's only one, I will often drop that variable, otherwise I'll keep it on. And in terms of discrete distributions, you've sort of seen me draw this before. We'll think of this as normalized histograms, if you will. So if there are 4 bins, this is the discrete uniform distribution, assigns the same probability of the outcome. This is a 4-sided coin, if you will. And this is the delta distribution that assigns all the mass to only one. All right. In terms of continuous random variables, let's just write this out. Okay, before we go there, a lot of times it's going to be useful for me to use shorthand, so probability of x equals to x. So this is going to be one shorthand, and sometimes I will just if it's clear that the state space is, let's say, 1 through k, sometimes we will write this as P of x altogether. So for example, we can write probability of 1 just as P1, right? Probability of state 2 just as P2. The reason why we do this is often it's going to be useful for us to think of this as a vector in some k-dimensional space. So we think of the probability mass function associated with a particular variable as a vector in some k-dimensional space. And it's clear that this is not just arbitrary vectors. For example, in a 2-dimensional space, it is clear that they will need to lie on a line. So this is x1, this is x2, so this is, sorry, this is dimension 1. It's clear that P1 plus P2 has to be equal to 1, right? So the only this vector can only lie in on this particular line. This concept is known as the simplex. A simplex is denoted by these inequalities. It's a vector where pi is greater than or equal to 0, summation of pi equals 1 through k is 1, and that in a 3-dimensional space, for example, we will talk about a particular right, so this is a particular plane. There are 3 dimensions. This value, each one of the points on that plane is a particular probability mass function. Right? So these corners, for example, this is, let's say, 1, 0, 0. It means that out of the 3 possible outcomes, only the first one happens. Right? This corner is 0, 1, 0. This corner is 0, 0. So each one of those are delta distributions. Somewhere in between, you have a point that is 0.5, 0.33, 0.33, 1 over k, if you will. Right? So the completely uniform distribution. Okay. So the space of all possible mass functions on on a variable that takes 3 states is the simplex. And the reason why this is interesting is because often we will set up optimization problems over the simplex. So we'll search for these probability vectors that maximize entropy or some criteria or minimize some criteria. Right? So these will be constraints that will constrain them.
Is there a standard rule where to use small p and capital P?
There may be, but I'm pretty bad about it, so I don't know. So I tend to usually just put in small p's everywhere and hope that the reader will figure out from context whether I'm talking about, and as you'll soon see, I'll even do that for mass functions and density functions. Yeah, I'll have to look into that more. Maybe there is a standard. I know this is pretty standard, and this is the usual short form of that. Okay. All right. So this is all nice and easy. Discrete variables. This is a mass function. When you go to continuous random variables, this is discrete. When you go to continuous random variables, the random variable is basically mapping some sample set to a continuous output, right? So it's taking values from 0 to minus infinity to infinity or some continuous range. And what we'll talk about is a density function. So I'll use the same notation. I'll actually write probability of x, and by that, what I mean is it's a density function. So we're if you integrate this density function over the entire space of minus infinity to infinity, that would be 1, which is roughly the analog of the summation of the mass function.
Sorry, what is the symbol next to the x?
That, sorry, that's the capital omega, so I use that for
okay, thanks.
sample space. So the space of all possible outcomes, which you're mapping to a continuous number. If you'd like to not think of that, just think of x as taking a value in a one-dimensional space. Okay, and you're familiar with in most of the things that I've been doing in class. I'll often end up drawing sort of these continuous things, and I often say the density function. So you're familiar with the Gaussian density function, for example, that has been in there. Okay. Let's see. The thing that we will often use is the idea of, so this will be pretty heavily used, the idea of expectations. Okay, you have some function f of x. X is a random variable, so any functions of that are also random variables, right? And functions of that can be anything. The example can be f of x equals to x, f of x equals x squared, x cubed, whatever you have. It could even be the log of x, or log probability of x, or any such function that you're constructing. And we will use this notation, expected value under p of this function f of x. Right, so oftentimes we'll explicitly put, so here's the variable, that's the function of that variable, and here's the probability mass function or density function that we're working with. Right? Sometimes we'll talk about the same variable but two different probabilities. So there'll be expectation under p, expectation under q. But when it's clear that there's only one probability, we can sort of drop that. So for discrete random variables, this is summation over the entire sample space or the output range. P of x, f of x. This is for discrete random variables. And for continuous, we're doing integration from minus infinity to infinity. P of x. Okay. Yes.
Is the range of f of x continuous or is it discrete?
Is the range of f of x continuous or discrete? Doesn't really matter. So x is, so in this case, x is a discrete random variable, and so you can only poll f of x at a few discrete places, right? In this case, x is a continuous random variable, so it's an entire continuous function. Okay. A lot of times, it's once, especially in the was there another question? Especially in the discrete case, it is often useful to think of this as an inner product of two vectors. It's p1 through pk, the vector that we talked about, and a vector consisting of all the f values. So f1 through fk. So k is the possible outcome. Right? So you can think of expectations as inner products in this k-dimensional space. And that tells you that if you're trying to maximize or minimize expectations with respect to some functions, you can sort of set it up as a linear program over a simplex. Find me a probability distribute mass function over this variable that takes k states such that it gives me the highest expectation with respect to some function. So the picture that we drew was, there's, let's say, some 3 values. There's some simplex, and there's some direction this time. That direction will be given by the vector f, so f1 through fk, and you're sort of optimizing in that direction, but you're constrained to lie on the simplex. Sometimes you can set optimization problems like that. Okay. Okay. now that we have the language of expectations, here's the standard notation that we use for means and variances, right? So mu will be expectation of just x, and your variance, so the variance of x we define as the expected value of x minus mu squared, and you've already done derivations of this, right? So you know how to work with these. Okay. Okay, here are the three important concepts that we'll have to get through that will play a strong role in some of the algorithms that are coming. So the idea of marginal distributions, or the concept of marginalization, the idea of conditional distributions, which we were already alluding to, and Bayes' rule. So let's first think of the idea of joint distributions in discrete spaces. So here are three random variables. They each take 1, 2, 3, 4, 5, 6 states each. And so in terms of, as an implementation person, you should think of the joint distribution as a multi-dimensional matrix. Right? So it's a 3-dimensional array. If you're holding 10 variables, this will be a 10-dimensional array, if you will. And every cell or element in this is one particular assignment to all random variables, and that gives you the probability of the joint assignment. Right? And the definition of probability is telling you that the sum of this matrix that you're holding has to be 1. Okay? So this should already tell you why joint distributions are going to pretty quickly become, computationally speaking, a problem. You're not going to be able to hold large matrices in memory. Anytime you have to perform operations, this is going to be, if each one takes k states, this is going to be k to the number of variables. We're not going to be able to hold such large matrices. We're not going to be able to perform operations on such large matrices. The thing we're going to be interested in is often getting the probability of a single or a subset of variables from joint distributions. Okay? And this is where this is not an axiom. This is a direct result of one of the axioms. Right? You can just do an extremely simple manipulation, and the fact that the probability of an event can be written as an event can be written as an intersection with something and its complement, and you just have to read out that the probability of an event is A and another event and some together with the probability of A and the complement of that. And when you apply this to the space of random variables taking multiple states, this just means you're summing over all configurations. Okay. In terms of actual implementation, this is where that picture comes back into view again. So if you think of a 3-dimensional array holding the joint distribution over those 3 variables, if I ask you for the joint distribution, for the marginal, in this case, marginalize out, this operation will be marginalize out z. That's the 3rd dimension. That's the, where is it? What happened?
Height is that?
Yeah, that should be. Yeah, there's a mistake. This should be y. Okay.
It's okay.
So this is basically addition of the slices in the dimension that you want to marginalize. And that's what this is saying right here. So it's the marginalization operation. It should be pretty clear that if we are holding a joint distribution, if I ask you for a marginal for a single variable, first of all, the memory requirement of holding that joint is, let's say if each one of them takes k values, then it's k to the n if there are n variables. Right? That's the size of this matrix. If I ask you to marginalize out everything other than one variable, so finding the marginal for one variable, it should be clear that there's one summation over this variable, one summation over this variable. So you're doing n minus 1 summations. Each one of those summations is over k items. It's k to the n minus 1. So that operation of marginalization is order k to the n minus 1. Right? So that's an expensive operation, going from the joint to the marginal. Okay. So manipulating such arrays would be difficult as well. All right, and so let's talk about the idea of conditional probabilities. In fact, it is so natural that we were already jumping to that idea. It's this notion, here's the notation that we will use. This will be a full notation. And notice that people often drop in fact I'll do that as well. Like this shorthand is essentially that, right? So random variable. All right, let's take a minute.
Make sure it's an axiom. 3 people per turn. That makes
Street event. That's right. That's what you found. And then from there you can find it. That's what I use. Technically, there's no difference between the street variable and when I'm writing that, I have to write in my head. Then use that and drive let's restart. Okay, so we're talking about conditional probabilities. And the way to think of these is, especially this notation is going to be very relevant because what we're going to do is we're going to build probabilistic classifiers which will essentially learn from data what probability of y given x should be. So given a particular configuration that I've never seen, I need to predict how likely is this email to be spam or not spam. So this will be a number between 0 and 1 for the spam case, and you will ultimately threshold. But the way to think about this, what do you believe about this state if I tell you something about this other variable? Right? That's a semantic interpretation of that statement. So to follow up the thing that we were talking about, the probability that Rafael Nadal wins French Open in 2015. So 0.9 was crazy. Just a priori, so this is extremely difficult for humans to do, right? Because you already are conditioning on a whole bunch of information. So for example, what if I were to tell you that Nadal has won French Open 9 out of the 10 times he has played there? Right? So if there was some suggestion that let's look at past data. That seems to suggest 0.9 is pretty great. That seems to suggest there's a 90% shot. But then if you also know that Novak Djokovic is ranked #1, he's just won the Australian Open, things are going to be tough. But the third most important thing is I offered a similar analysis last year in the Nadal Open. So clearly that should affect your... I've been doing this 3 times, Nadal has won 3 times. So that should have a role. Okay, so in terms of formalizing that intuition, we're talking about the worlds where this event P has already happened. That's the information that you're conditioning on, and we're talking about the probability of the fraction of worlds where A is true. And this intuitively can change your interpretation of what's going on. So in this case, in this example, H is headache, F stands for flu. So and this is the entire set of outcomes. So headaches are rare, flus are rare, but if I tell you that you already have a headache, then we are only interested in this particular region of space, right? So it's this region divided by all of headache, and that's a pretty large proportion. So certainly your conditional probabilities can change with this intuitive application. From an implementation perspective, if we come back to this picture that we've been holding, when you condition on a particular value of a variable, we're asking you to slice that matrix, that multidimensional matrix, and hold one variable fixed. And because the definition says the joint, the conditional is equal to the joint divided by the marginal probability of that variable that you're conditioning on. If you think about what this is, this denominator is just summation over all values of x and y. That's the marginalization definition. And so you're slicing this. You're only concerned about this slice because z does not change. This is the z-axis, right? Z does not change, but the denominator is sort of renormalizing that slice. Okay? The entire matrix, the three-dimensional matrix, sum to 1. This slice obviously by itself does not sum to 1, but when you renormalize by adding up those numbers, then it sums to 1. So it becomes a distribution. Okay? And it should be clear that just like marginalization is difficult, conditioning is also going to be an expensive operation. All right. The very definition of conditional probability is going to lead to an interesting definition of chain rule that we're going to apply extremely frequently. So the probability of y plus little y divided x equals little x is equal to going to be the joint probability of y equals little y comma x equals little x divided by the probability of x. That definition is going to lead to something that we're going to refer to as chain rule. And in fact, in some models, we'll do recursive application of chain rule. So chain rule is just going to be probability of y equals little y x equals x is just okay. Feels pretty trivial. Feels like we've just manipulated a few things around. We've just sort of moved the denominator around a little bit, and we get to call that's a new identity. But the reason why this is going to be often useful is you're going to construct. You're going to collect some d-dimensional features. So xd is equal to little xd. You're going to reason about this joint distribution, and we will need to recursively apply this rule. So when you apply it once, it's going to become x2 is equal to little x2, comma blah blah. xd is equal to little xd times condition on x1 equals little x1 times probability of x1 equals little x1, right? And we will apply chain rule again to this side, to this particular term, right here. And what we get is probability of x3 equal to little x3, over xd equal to xd, and to term that x2 and sorry? Oh, condition, yes. Thank you. Condition on x2 equals little x2 and x1 equals little x1. Notice this is just a recursive application of that. The world was already conditioned on x1, right? X1 already happened. And so now you're just conditioning on one extra variable. You're just applying this rule once more. Right? That's the sort of intuition that people like. Probability of x1 so you get 3 terms. You continue recursively applying that all the way to d terms, and what we'll get is probability of xj equals little xj divided x1 equals little x1 all the way to xj minus I'll say j equals 1 through d with the abuse of notation that j equals 0 is just nothing. Yeah. So we're going to end up with these terms like these. So a feature, this is all features depending, if I told you what one variable was, what do you believe about the other variables? If I told you what two variables were what their states were, what do you believe about this configuration of all the others? Right? And then you can sort of write down. One of the things that we're going to ask you to think about and analyze is that we argued that this term right here, this is pretty heavy. Right? This is, just to save this, is order k to the d, right? If every variable takes k state. We're going to ask you to think about this analysis and think about whether this decomposition saves you any space. Right? Turns out it's not going to save you any space. It's actually going to be heavier to do that. But dropping certain terms from the right side is going to end up saving space. Okay? And that's going to be the basis for factorized models or graph type models. The definition of chain rule, which is right here, is also going to lead very naturally to the idea of independence. So if these, the idea of independence is going to be, I tell you something about, today is sunny and I ask you to predict is Nadal going to win 2008, right? Clearly, me telling you this variable is not going to change what you already believed. Or if it did, then you're not a very good classifier, right? But hopefully the idea is that that's not going to change. So there's going to be this, that definition is going to lead to y little y, x equals little x, if is equal to probability of y equals little y, then we'll say, x is independent of y. And this is the notation that we use. X is and this is going to be the same thing as saying probability of y equals little y given x equals little x is the same thing as y equals little y. So the joint will factorize into marginal. And by factorize, I mean that this is a joint matrix and I can write it as a product of individual terms that only contain, like each of these individual terms contain fewer variables than this one, right? It should be clear that this one, if each one of the states take k, each one of the variables take k states, then this takes k squared entries to store in a matrix, right? Maybe you can be fancy by not storing the last one because they all sum to 1, right? So it's a k squared minus 1. But these guys each only take k each. So this is 2k minus 2, if you will, numbers to store in a table. So independence is going to end up saving you space because you're going to end up storing these individual vectors as opposed to the matrices, and it's also going to speed up algorithms. Here's a linear algebra view of the same thing. Independence, when thought of as a matrix, you can view it of two random variables. You can view it as an outer product of vectors, where this is p of x, that's p of y, and it's clear that any entry, xi, yj here is just a multiplication of the corresponding entries. Okay. So as I mentioned, the notation that we follow is this: x is independent of y. This is formally the notion of marginal independence, in the sense that you can extend this to sets of variables. X can be a set of variables, y can be a set of variables, and you say this set of variables x1 to xd and y1 to yn. This set is independent of this other set, and that's the shorthand. If this equation is satisfied. And this is going to be extremely important because, in fact, some of you usually end up people making this mistake in the homework that's coming. This is not a single equation. This is a set of equations, one for each value of x, one for each value of y. Right? If x takes k states, y takes k states, this is k squared equations. If any one of them does not hold, you do not have independence. Right? All of them have to hold. If a subset of them hold, that's formally known as context-specific independence. In the sense that I know this, only with this one particular configuration, if I know that y is set to this, then in that case x and y become independent, but not otherwise. Okay. And this notion can be extended to the idea of conditional independence. So we will, x can be a set of variables, y can be a set of variables, z can be a set of variables. And instead of saying x is independent of y, what we'd often say is x is independent of y given z, which will essentially mean, if you think back to that equation, we mean the probability of x comma y, this time conditional on z, factorizes into two terms. Probability of x given z and probability of y given z. Okay. Between this and the previous slide, nothing has changed except in this equation on the left and right side, I just added, the entire world is conditional on z already happened. That's what we're talking about. And so we're reasoning about x and y under the assumption that z has already happened, and also on the other side. That makes sense? You'll see this idea in the concept, in the example of naive Bayes, where we will talk about if I tell you what class we are talking about, the different features are going to become independent, and that will lead to simplistic assumptions. And we'll cover that in the next video. Okay, so conditional independence is going to end up being handy. Okay, so finally, the thing that we're going to see a lot of times in this class, Bayes' rule, extremely simple to the point that it's, so far what we've done, it's nearly trivial to derive Bayes' rule. It's just chain rule applied twice in two different ways, right? But it ends up being the source of a lot of use and a lot of controversy. So what is... Alright, chain rule stated there. Let's apply it in the other direction. Probability of x equals little x, y equals little y times probability of y equals little y. Right? No magic there. Here, if you just swap the order of x and y, you just get that. Right? And that is what leads to Bayes' rule, which for our case is going to, with our special interpretation of the variables, is going to lead to extremely interesting y equals y, x equals little x equals probability of x equals x. Okay, that is all of it. That's Bayes' rule. The terms in Bayes' rule are going to play, with their usual meanings, an extremely important role. So this we will refer to as a posterior. What do you believe about the classes after I have already told you the input? Right? As to be contrasted against this term, which will be referred to as prior. What do you believe about the classes before you see any data? Is some person just more, is cancer just likely, more likely or less likely than not having cancer? Right? This term is what we're going to refer to as, the likelihood. And likelihood is going to be an important concept because the likelihood is going to be, if I tell you that this person has cancer, does that make his symptoms more or less likely? Right? So if, we already know what has happened, right? This person has come in, he's exhibited some symptoms. So now we're talking about the probability of x, and what if I swap y in and out? What if I try to explain these symptoms with, the class 0, class 1? Do they have cancer or not? And if that leads to two different probability values, notice they do not have to sum to 1. Right? This time we're just swapping y in and out. Conditional probabilities sum to 1 over x, they do not sum to 1 over y. So I can get a vector which is of the length equal to the number of states that y takes, and it can be these probability values which are all likelihoods. And the higher likelihood does mean that you have found a reason, you know, a category that explains these features. Right? But you still have to multiply that with how likely that category is to happen in the first place. You can really explain, so you can construct a vector of likelihoods, probability of x equals little x, little y equals 1, all the way till x equals little x, little y equals k categories, k numbers. It may be the case that, you know, you have some category in there that perfectly explains somebody's symptoms. You are sneezing, I think that you have, you know, some nasal cancer or something, right? You know, because everybody who has nasal cancer constantly sneezes. Gotcha. But you know that class is maybe just extremely unlikely to happen. So we should downweight our beliefs to ultimately reach a posterior which says, you know, even though you're sneezing, you know, yes, the probability of you having nasal cancer has risen, but it hasn't risen extremely high. Right? We have to still see more data before we can make that conclusion. Right? Yes.
Is that where the calibration come from what you were talking about earlier?
Yeah, so the calibration issue is going to come from the choice of this. Where do your priors come from? The priors are by definition, you know, X is data, Y is the thing that we're trying to predict, and I'm asking you to construct something that you have no data for, if you will, right? So either, and it is possible to sort of quote unquote learn your priors, and that's going to be a whole other thing, but a lot of times this is where domain knowledge is instilled, right? You can just, I know I have seen this, and I don't know how to explain it, I can't write it out in data, but I know that this is just less likely to happen than others. But if those priors are uncalibrated, so will your perceivers. So for example, if you notice that if I set the probability of y of some category to 0, if my prior says that category just, yeah, it can't happen, ever, right? It doesn't matter how much data you see, it doesn't matter how much that category explains this data, the posterior is still going to be 0, right? You just cannot change your belief because you started with a 0 probability, a 0 prior. That makes sense? Okay. The third term in here is going to be sort of the evidence term. And often we're not going to stress too much about this because this will just play the role of a normalization constant, right? Because this is just going to be summation over y. Right? So it's essentially just the numerator. What did I do? Yeah, that's right. Yeah, so in that, and you can extract out the numerator from it. Right? So it's essentially just the numerator summed over all categories. It's going to be, so we're often going to talk about proportionality, and we will often drop this denominator. Right? So it'll just be the product of these two terms is proportional to the posterior. The prior times the likelihood is proportional to the posterior. Make sense? Yes.
Does that mean just all the? Could you replace it by px equals x?
Could I replace what with what?
The denominator, because that's the summation of px and y for every single
Y.
For every single y.
Yeah.
So wouldn't it be
Px.
just px?
Yeah, that's what we started with. Yeah, that's essentially what chain rule told us, right? It was chain rule in two different directions. We applied that. We got denominator px equals x. And what I was just saying was px is the same thing as I can add an extra term y equals little y, and I can sum over that, and then I can apply chain rule to each one of these terms, right? So I can say px given y equals little y times probability of y equals little y.
Okay.
So what I was trying to draw a distinction, similarity was this is just the numerator summed over all classes. Just a normalization constant. Okay. So it's extremely simple, but it's important to note that using Bayes' rule doesn't mean that you're a Bayesian or you just perform Bayesian analysis. Bayes' rule is a direct consequence of elementary assumptions that you made, right? Sorry, the assumptions aren't elementary, they're the foundation of all probability, but elementary analysis that you get from those assumptions. The place where frequentist analysis and Bayesian analysis is going to separate is on the construction of priors and the use of priors. If you're constructing priors and you're constantly talking about posteriors and you're coming up with sort of confidence intervals based on posteriors, that's going to be a Bayesian analysis, and the frequentist analysis is going to be about repeatability intervals. Can I give you a 95% confidence interval, which means I tell you that you want to estimate some parameter, I will tell you that here's the value of that parameter plus here's a 95% confidence interval, and my 95% confidence interval is going to mean that if you repeat your experiment, if you repeat your data set 100 times, 95 of them, the parameter is going to lie in this range. Right? It's a frequentist guarantee. The Bayesian guarantee is going to be, my belief says that here's the range that the parameter lies in. Your belief may be uncalibrated because the input prior was uncalibrated. Okay. So we'll meet these three terms over and over again. The thing that we will often use to measure the amount of uncertainty in distributions is entropy. What's entropy? Anybody want to tell me? What?
Uncertainty.
Uncertainty, degree of uncertainty in a distribution. So the definition is right here. You're summing up over P of X of log probability. There's a little intuitive explanation that I often find useful. So notation is going to be h of p or sometimes h of x. So sometimes we'll talk about if there's only one distribution that we know we're working with for this variable, we'll talk about the entropy in this variable, in the distribution associated with this variable, but often we're going to talk about h of p. Right? And that's negative of p of x log probability of x summed over the entire domain, so 1 through k. This is for the discrete case. Okay. The way to think about this, and this is a connection that you can keep in your mind. This is probability of x minus log probability of x, right? Summed over all x. So far so good, and this starts to look like the expectation that we did, right? So this is the expected value of this function. You're summing over all things. This is the expected value of a function. Let's call this a surprise function. Right? This function is telling us, so let me say s of x. This function is telling us how surprised you should be in an experiment when the outcome is x. Right? And this is a good function indicating surprise because it's sort of doing the right thing. Here's how the log function looks like. Right? This is what log of x is, crosses over at 1. This is minus log of x. Probabilities are always between 0 and 1. So if it's an event that always happens, you're never surprised, right? Thankfully. If it's an event that is rare and rare, the amount of surprise is exponentially up. Right? Does that make sense? If I tell you that I won the lottery and I'm quitting Virginia Tech, you should be surprised. Perhaps not at the implication, but perhaps at the winning the lottery part. But if I tell you that there's a test next week, you should not be surprised, or something like that. You should be a little bit surprised. There's not a test next week, but you shouldn't be that surprised, given how I've portrayed this. Okay, so it's a surprise function. Why is it log? Because log is nicely additive. I can give you two independent random variables, and log they have nothing to do with each other. The joint distribution factorizes, and the amount of surprise just adds up. That's sort of, it's the nice thing to do. It's sort of the intuitive thing to do. So this is the expected surprise over all possible outcomes given the probability, how frequent, how likely is that outcome. Yes?
Can you use like another function besides the log, even though it wouldn't be as convenient, or is it, I guess there are other reasons why?
I would, but Shannon already solved this whole entropy thing for me. So there's fundamental connections to the amount of information that you can convey over a channel, and sort of the nice thing. The base of the log doesn't really matter. You can change that definition, but it's 2 or natural log, that doesn't matter. But in some sense, the log sort of plays out nicely, because if you're trying, in sort of the information and the communication world, if you're trying to convey a symbol, then the log number of bits is the amount of bits that you have to convey, and it's so that's the right thing to do. In our case, yeah, if we're just, for us, this is a measure of uncertainty in a distribution. There is no connections to communication or things like that. You could sort of work out different things as well. It should be obvious that here's a distribution that this is 3 bins. This one has probability 1. This one is 0, 0. The amount of the uncertainty in this case is probability is 0. 0 log 0 will define as 0. You can check the limits. That's going to work out. 1 log 0 is also going to be 0, and 0 log 0 is also going to be 0. So the sum of those 3 terms here, the uncertainty is going to be 0. So this is about as certain. This is about as certain you can get in a distribution. There's no uncertainty here. Fully uniform distribution is going to be 1 over k. You can show that it's just 1 over k log 1 over k negative summed over k, and you're just going to get back log base 2 of k. Right? So this is the maximum amount of uncertainty that you can capture in a discrete way. A fully uniform distribution. Okay. All right. Let's see. Okay. Yeah, let's just do this. Let me just finish up this. You already met this concept in your homework 0, but we are going to use the idea of KL divergence. So entropy we're going to use to measure the amount of uncertainty. And one of the things that we'd like to do is have, the distribution that we will be interested in is probability of y given x. This is a distribution that we're going to be interested in. And we'd like to have as little uncertainty in this distribution as possible. Right? Little uncertainty in this is going to mean whatever input that you have given me, has correctly nailed down. Like there's no confusion in the classes that I give you. Right? So we're going to seek low entropy in this sort of distribution. High entropy in this conditional distribution is going to mean we have no idea what's going on. The input that you just gave us could be any of these particular categories. The concept that we will use repeatedly is KL divergence, and we'll use that to measure the, not distance, but the divergence or the amount of difference in 2 particular distributions. You've already met this in homework 0. You've proven why this cannot be a distance. It's not symmetric, right? But it's this particular beast, the expected value of log probability of x divided by q of x. Right? So it's this ratio that you're taking an expected value of. The reason why this is going to be interesting is, if you think about it, this is a ratio of p of x to p of q of x. Thank you. So what we're going to try and do is, here are 2 different distributions. They're over a continuous space, but you can think, the same concept will hold over discrete spaces as well. This one is p, that one's q, right? They're slightly spread apart, and we'd like to quantify how different are these 2 distributions. What this thing is doing is this is taking a ratio of the 2 density functions, right, of the 2 distributions. If the ratio is greater than 1, then the log will be positive. If the ratio is less than 1, then the log will be negative. Right? So here's the. So that thing, that curve that we're looking at, that it's the log ratios of of the two distributions over the space of X as shown, right? And then what the summation or the summation P of X or the integration, if they are continuous, is just doing is it's doing an area under that curve, right? It's doing a weighted summation of that. And what we'll find is that as you have two distributions, so these two are close, these two are far apart, and there will be sort of a bigger area to integrate. So if we're computing the distribution, the KL divergence to this P, these three curves will have higher area, and it will be clear that the green one is farther apart from the distribution. Okay? Importantly, we will think of KL divergence as a directed measure, and that's going to be important. This divergence of Q from P, how far apart is it? Okay? And it's therefore, you're always going to have to be careful that Q has to have, in order for KL divergence to be defined, Q has to have support at least where P has support. They both cannot be zero simultaneously, otherwise this concept will be. Alright, let's stop here. So what we'll do next time is, we've gone over essentially all the tools we need. What we'll do next time is start with estimation and the idea of maximum likelihood, and maximum posteriority, and posteriority bias. And that will be a lot of what we need to answer the question, I think, what we